Hey guys, welcome to the office hour. So I will be going through the assignment 4 today. So actually, let's start by looking at the code. So we have a data structure called decision node here, where it has a left child and a right child. And so both the left child and the right child, they are different decision nodes. And you either have a decision function here or a label. So if you reach a node and there's a decision function, if the decision function evaluates to true, you go to the left, and if it evaluates to false, it goes to the right. And if it has a class label, then you can just basically label your data according to the class label without worrying about the decision function. Okay, so we'll take a look at part 1 of the assignment. So here you want to build out a binary tree by hand, looking at this table here. So what you do is you split the decision out of a feature you choose. Say if I want to choose the decision function to be A1, then say if A1 equals to 0, we go to the left child. And if A1 equals to 1, we can go to the right child. And then we can split further on A2. And so on until you can separate out the Y classes. So Y equals to 1 and 0. So for example, you can see here, like if A1 is 0, you probably want to go to, say, a left node. And then so we are left with this one, this one, this one, actually these three. All right. And then you can split further, say on A4. Actually, A4 is not a good split, right? Because you get ones and zeros here. So you want to choose the split that gives you only ones in one branch and zeros on the other branch, then you're done. So you can have different layers of the tree. And it asks you to use as few features as possible, right? I think in this. So you don't want to like enumerate all the possibilities in your tree, the tree, because the tree gets too big that way. So you have an example here of on how to build out your node, your decision tree. So you just have a root and then left, right, and then just building all these nodes for different layers by hand. And then that should be pretty straightforward. And for the next part, precision, recall, and confusion matrix, these should be pretty easy. You can just find their definitions, and yeah, they're pretty easy to calculate. And then next is the Gini impurity and Gini gain. So for these, you basically are given a list of classes as an input. And let's do this. And yeah, so you have the Gini impurity. The definition is here. You want to, so it's basically this one here. So it's 1 minus the sum of the probability of all your classes squared. So pull up the screen share. So let's say if you are given a class vector 0, 0, 1, 1, right? Say the probability of 0 is 2 on 4, right? Because you have 2 zeros out of 4 total samples, right? And then P of 1 equals 2 over 4. So the impurity would be 1 minus 2 over 4 squared minus 3 here. That's the sum of all your probabilities squared. Okay, that's basically how you calculate it. And let's get this back. And yeah, so there's you're also required to do a Gini gain, which is simply here. So it's basically the information gain, but instead of the entropy, you use the Gini gain. So it's the Gini gain of the parent minus the weighted sum of the Gini gain of the children. I mean, not Gini gain, the Gini impurity of the children. And so you should basically, the parent splits the sample into 2 parts, and then you weight those 2 parts by how many samples they contain, and then you calculate the Gini gain for each of those 2 parts of samples, and then you add them up, and then you take the difference between the original data and the split data to get the Gini gain. And so the next, we get to the main part in the decision tree learning, where you're required to complete a class. So let's take a look at the code. Okay, so this init function is given, and then the fit is uses the build tree. So in this build tree function, the input is a list of features and the list of classes, and you specify a depth. So the features variable is basically a matrix. So each row is your list of features for that sample. And then the class is basically a list where it shows you the class of that particular sample. So what you want to do here is you want to build a node, basically decide on which features you should build your node upon and what's the split. So using that split, you can partition your data into half. So you want to basically split the classes as much as possible. You can calculate the Gini gain. You can do the maximum Gini gain between before the split and after the split. So after you split the data into half, one half goes to the left node, and then the other half goes to the right node. And then you can repeat the process. You can split on some feature again on the left node and split again on the right node. So you can do this via a loop or a recursion. It's up to you. And so many of you ask if you can use the same feature. Yes, you can. Of course, you can split based on feature 1 in your root node, and then you can split on the feature 1 again in the left or right node. So that's the same as partitioning like the same feature into different intervals. And so for classify, so you are given a list of features without the classes, and then you want to determine what classes they are. So what you do is you use the tree you have built, and then just follow the tree, go along the tree until you reach a leaf where there should be a class label, and then you just take that class label for the classification. Okay, so next is, okay, generating k-folds. So what you want to do here is to split a data set into a training and a validation sets. So for example, if I have 1, 2, say this is our feature set. And so let's call this features, classes, say labels. Okay, so I have 5 features and 5 labels. Let's say if k equals to 5, what I want to do is return a list of folds. So what does each fold look like? Each fold is a tuple with a training set and the test set. Okay, so a training set would look like this. So k equals 5, right? So we take 4 samples into the training set. And okay, so tuple, and have a list of features and a list of labels. So that's what a set looks like. And then the test set is just the remaining data. Okay, and so that makes a fold. Okay, and so you want to return a list of k-folds. So you split your training and testing at different places to get 5 of these folds, and then you return them in a list. Okay, so if in some cases the number of samples does not match, it's not divisible by k, then you can just, I think the testing script requires you to put the remaining samples into the training set. Say, for example, if we have 6, then you should put extra sample into the training set. And that should work. Okay. So let's continue. So random forest. Okay. So for the last part of this assignment, you want to build a random forest. A random forest is basically a list of decision trees. And so you have 4 different parameters when you're building a forest. Number of trees in the forest, and the depth limit of those trees, an example subsample rate, and an attribute subsample rate. So fit and classify, these are functions which they do the exact same thing as when you do the fit and classify in your decision tree. So how you use the example sample subsample rate and the attribute subsample rate is that, for example, let's use our old example here. So you want to subsample the number of the data set according to the example subsample rate. For example, if the example sample rate is 0.8, then you want to only select 80% of your sample when building a tree. And say, for example, attribute sample rate equals to 0.5, and you want to select 50% of your attributes when building a tree. So in this example, we would be selecting 0.8. Say we'll be selecting like 4 or 5, depending on how you round it. So 4 or 5 samples out of the data, and then attribute sample rate. We would be selecting 1 attribute when building our tree. So each tree you build should select random samples and random attributes. So for one tree I can select the the first attribute. For the second tree, I can select the second attribute, and which attribute you select should be determined randomly. Same with which samples you select. And then each time you build a tree, you add it to a list, which is this self.trees. This is a list. And then in your fit function, you just populate this list with trees. And then in the classify function, what you do is you're given a set of features, and then you fit these features into every tree in your random forest. And then you take a majority vote. Some trees might give you a 1, others might give you a 0. You see which one's the majority, and then you just return that classification. And so yeah, the next is challenge classifier. So you can, for this, you can set your parameters in your random forest and then just use that. Or you can apply some additional tricks to make your accuracy higher, like boosting, for example. And so yeah, you're not allowed to use any external library here, only your decision tree and random forest. And yeah, another thing to mention is that all the files in this assignment, the classes are binary, so either zeros or ones. I think that question many of you also asked. But ideally, your code should work for any kinds of classes, because when you're building your decision tree, it shouldn't matter if it's binary or not. And okay. So there's a last part, which is the vectorization, which is a preparation for assignment 5. And okay, so I will go through a couple of basic NumPy tricks for this. Okay, so basically NumPy is really good at vectorization because it's written in C to speed, which can speed up vector operations. So sorry, import NumPy. Okay, so for example, I have a list in Python. Okay, I can cast that into an NumPy array. And I can do operations between NumPy arrays. Into A plus B. So that's a lot faster than you writing a loop for I in and A. So for that loop, A plus AI plus BI, for example, blah, blah, blah. It's a lot faster to just use vector operations like this. And you can do a lot of tricks like A times B. So this will multiply your two arrays element-wise. And you can do an element-wise log like this. And then you can do whatever kind of operations you like. And also, you can do a plus 1. So NumPy detects the dimension of this, and it knows to add that you want to add 1 to each element of this array. All right, so you can do a times 5, also works, plus b. All this makes it very convenient. And so if you just do your operations entirely in NumPy arrays, you shouldn't have much trouble with the vectorization part. Okay, and if there's anything you don't know how to do, you can always just look up on the NumPy documentation, and these are really basic operations, like this array slicing, array operations. And finally, the last part is to return your name, which so that we know like who you are, like who wrote this script. And yeah, this is pretty much it. Okay, so if there's any problems, you can always ask on Piazza, and we'll try to answer as soon as possible. Okay, thanks guys.